So as I was explaining in the previous video, what we normally do a lot in petroleum engineering is to transform the X and Y axis of our data set. And then we try to look for a straight line because it's easy to extrapolate out into the future. So in this particular situation with this nonlinear data set, what we do is to take the natural logarithm of this time. So instead of time in days, we're going to be showing the natural log of time. So log of 50 is what we're going to have in this point. This will be log of 100 and so on. And this is what the result looks like. So just focusing on the green dots for a second, you see the green dots, which are the actual data sets, they get transformed and now they line up along a straight line. And it's easy to fit a straight line through this data point. And this will be the equation for the straight line. It's a function of x. So this is ax plus b, y equals ax plus b. So this is the intercept. And you see, if you extrapolate this all the way to the top, it will be around 1700. And the slope is minus 285. And this is the natural logarithm of time. So how do you predict production beyond this point in time? You just extrapolate this line further out. So when the log of time is 6, the oil rate will be this much. Good. So that's one way to get a straight line out of your nonlinear production rate plots. Decline curve analysis is one of the most common models to predict production performance in oil and gas industry. It is basically an approximation, and this is because what we do is we fit some equations, pretty simple equations, to the observed historical data, and then using these fitted equations we can make predictions out into the future. The three most basic decline curve models are listed here. The first, which is the simplest, is the exponential model. Even though it is the simplest, it's still the most commonly used because it is conservative. So you can get conservative estimates and hope your actual production performance will be better than what you get from this exponential model. The hyperbolic decline model is more generic. It's more applicable under a wider set of conditions, and so it's also commonly used, and the harmonic is the least commonly used. What is the main difference between these models? It's this B exponent. So when I talk about B exponent in the lab session, this is precisely what we're talking about. In the exponential decline model, B is 0. And for that reason, you don't see B show up anywhere in the equation. Small q is for oil rate. It could be for gas rate, but it's for rate in general. And big Q is for cumulative production. So oil rates, typically the small q, will be in units of volume per time, barrels per day, or stock tank barrels per day. Whereas big Q will be in unit of barrels because it's the total amount of oil that you've produced at a specific point in time. So big Q is the volume of oil produced over time, whereas small q is flow rate, barrels per time. So again, in the exponential model, B equals 0, so it doesn't show up in the equation. In the hyperbolic decline model, b can be anywhere between 0 and 1, not inclusive. So b has to be greater than 0 and it has to be less than 1. Whereas in the harmonic decline model, b has to be equal to 1. So that's why this is a more generic model, right? Because b can assume any value between 0, greater than 0 and less than 1. So it's able to fit more data sets, whereas some data sets cannot be fitted with an exponential model because it doesn't have the flexibility to capture the changing trends in the oil rate. Whereas same deal with harmonic decline, it is also not flexible enough in some cases to fit some production data. So that's why you will see many times hyperbolic decline is used. So you can actually almost match any data set that can be matched with exponential and harmonic with the hyperbolic. How? Just make b very close to 0 instead of using an exponential model, right? So it will replicate the behavior of exponential decline when b is very close to 0, and you can set b to be 0.99999 and use that in place of an harmonic decline. So very important to be able to program this hyperbolic decline. And of course, we'll start out simple. We start out with the programming of the exponential decline. As the name indicates, it's going to use an exponential function. So we need to be able to evaluate exponents in Python, right? And we'll talk about that when we get into the lab session. So take the exponent of the product of the decline rate, initial decline rate, and time. And if time is given in days, this initial decline rate has to be in percentage per day. So the product of these two terms has to be consistent, and it has to give you a unit of percentage, right? So if time is in months, then this decline rate needs to be in percentage per month, and we can make the conversions so that the product is consistent. If you integrate this flow rate over time, which is equal to this integral, what you get, so integrate it with respect to time, so this will be dt. What you get is this. So if you perform this integration analytically using what you already learned in calculus, you will obtain this value. And by the way, you are integrating within limits between time 0 and the time t. That's very important. That's how you will be able to obtain this value right here. And you will later see that you can also perform this integration numerically, like I explained. So if you have flow rate, curve of flow rate against time, we can find the area under the curve, right, using trapezoidal rule. And that area under the curve at any given time, say here, will be equal to this cumulative production calculated with this equation, provided this curve is exponential model, right? What if it is hyperbolic? Well, this is the equation you will need to program. Keep in mind, here you are raising what is in this parenthesis to power 1 over b. And we will be doing this calculation in the lab session. If you integrate this equation between 0 and t, right, integrate it between 0 and t with respect to time, this is what you get. And that's your cumulative production for the hyperbolic decline. And for harmonic decline, it's as simple as setting b to 1 in this equation, and then this b dit becomes dit, right? 1 over 1 becomes 1, and this is what you get. When you integrate it, this is what you obtain. And we will be programming these 3 models throughout this course. It's very likely you're going to have a midterm question that requires you to program these. So make sure you have quick access to this equation. You know where it is in your slides, because you will be programming this in the lab session. I can pause the video here and then we continue from here in the next video.